Black holes. These punctures in the fabric of the universe provide endless fascination and speculation. But what are they really? And how do they actually form? Most black holes are the remnants of massive stars, the ultimate triumph of gravity over light. Every star relies on a balance between outward pressure and inward pressure to maintain its shape and stability. When a very massive star exhausts its nuclear fuel, the star simply collapses under its own weight, forming a black hole. The center of a black hole is a singularity. All that remains of the star is compacted here to a point of infinite density. Surrounding the singularity is a spherical volume of space. Gravity is so strong within this sphere that nothing, not even light, can escape. The outer edge of the sphere, the event horizon, is the edge of no return. How do we look for black holes if they can't be seen? The first evidence of a black hole came in 1974, when astronomers detected a tiny source of X-ray light flickering in the constellation Cygnus. Although tiny, Cygnus X1 was many times more massive than our Sun. Since it did not shine with visible light, it had to be a black hole. Swirling matter and jets of energy just outside the event horizon often frame a black hole. This whirlpool of gas is an accretion disk. It can reach temperatures higher than 1,000,000 degrees. X-rays and gas emitted by the accretion disk can jet out from either side into space. These images are thought by astronomers to be an accretion disk around a gigantic black hole in the center of a distant galaxy. Closer to home, millions of stellar black holes may be among the few 100 billion stars in our own Milky Way galaxy. The nearest black hole may be only 30 light years from Earth. In the early 20th century, Albert Einstein formulated a new concept of gravity. General relativity explained gravity as the warping of space by matter. Space stretches like elastic. Matter determines the shape of space. Any massive object will pull the fabric of space towards itself like an hourglass. The extreme gravitational warp of a black hole stretches space towards its own center. Without matter to curve space, light rays would travel in a straight line. When space is warped, light traveling through it would follow a curve. This causes space itself to act like a gravitational lens. In our everyday world, nothing can warp space to this extreme. But imagine a mini black hole in front of a familiar scene. Although nothing in the background actually moves, buildings appear to bend. Out in space, a black hole would distort the pattern of distant stars in the same way. What would it be like to fall into a black hole? We could remain quite close to a black hole without actually falling in. Gravity is strongest near small stellar black holes, where we would be pulled and squeezed into a thin strand by the stretched space surrounding the hole. Once the event horizon is crossed, only blackness would loom towards the center. and in less than a thousandth of a second, our atoms would be crushed to infinite density at the singularity. For thousands of years, humans have contemplated the universe, but only in the last 100 years has our understanding included black holes. What we have learned so far already raises many questions, and yet our current knowledge of black holes is only a small step in a course of discovery that will change the way we understand our universe forever.